Okay, let's continue our study of electricity. In the previous lecture video, we talked about how the electric force and the gravitational force have the same type of equation that tells you how strong the force is. And we talked about how there are similarities as well as differences between the electric force and the gravitational force. Very often with gravity, we talk about something called the gravitational field. And so the way that works is if you have a planet and you have a moon, say, we can say that the gravity exists between the planet and the moon. But we can also say that the planet is creating around it a field in space, and that the moon is responding gravitationally to the field rather than to the planet. It's just another way to look at it. And it turns out that in certain contexts, it's more convenient to look at it that way. And it turns out we do the same thing in electricity. We talk about, rather than always this charge is attracting or repelling that charge, we talk about the charge creating an electric field around it in space. And that electric field, if you put another charge in that electric field, it's going to interact with that electric field and either feel an attractive force or a repelling force. And we typically draw electric field lines as we can see in these figures here. And so you can note here I've got a positive charge and the field lines are going radially outward away from that positive charge. And the reason for that is these field lines, they follow the way that another positive charge would go. In other words, if I put another positive charge right there, it's going to be repelled and it's going to go off shooting off in that direction. And if I put another positive charge right there, it's going to be repelled by the charge in the middle and it's going to be shot down. And so these electric field lines show you which way the force would be on a positive electric charge. By the way, if instead of a positive charge here, this were a negative charge, these electric field lines would go inward because a positive charge right here would be attracted to a negative charge and would be pulled in this way rather than repelled. But basically, the electric field lines show you sort of a pictorial way, the way that the attraction or the repulsion will go. With these little arrows, it shows you how they go. And so you can see here we have two separate charges, one positive and one negative, and the electric field lines start on the positive charge and they go around and they end up on the negative charge. And in every case, this is sort of the direction of the force on a positive charge at that location. So if I put a positive charge right here, you can see that arrow is pointing to the right. If I put a positive charge right here, you can see that force is kind of pulling it into the negative charge. And so it's attractive or repulsive. The combination of those two charges together create this sort of pattern of force. Here we have two parallel plates that are oppositely charged. And in the center of the plates, we can see that the lines are straight. They're going straight across. And over here, we can see what I was talking about. If it's a negative charge, the electric field lines are going inward. In this figure, we can see some bits of thread that are suspended in an oil bath. And these threads, they line up with the electric field lines. And so you can see here, we've got two charges. And in A, it says they're equal and opposite charges. And we can see, just like in that previous slide, the field lines, I don't know if you can see it, I hope you can, but you can see that the lines of the threads, they're curving around. And so there's a thread here, it's moving away, and then it's moving towards, it's curving around. Up above, you've got that same, and it's symmetric. And right in the middle, it's going straight across. And so you can see these sorts of behaviors. This is showing you the direction of the electric field lines. Here in slide B, we have equal charges of the same kind of charge. So for example, maybe they're both positive. And I don't know if you can see that, but the field lines are going away, but right in the middle, they're kind of doing something like this. They don't actually cross one another, but they're turning like that. And but over here, they're just kind of going straight out, or straight in if it's a negative charge. But over on this side, you can see they're curving, and over here, it's kind of curving like that. Here we see in slide C two oppositely charged parallel plates. And again, you can see in the middle, the lines are straight across, but towards the edge, they kind of curve around a little bit, which is interesting. That curving at the edges, there's a word for that called fringing. We say the electric field lines are fringing. You don't really need to know that, but I just sort of throw it in as an FYI. And this is kind of interesting. Here you have a circle and a plate, and you can see these field lines are curving towards the circle from the plate, or vice versa. Now, here we have three different oddly shaped conductors. Something like, it could be pieces of some kind of metal like gold or lead or something like that, something that's conductive. And here we have one that is a sphere, one that is a cube, and then one's this sort of oblong egg type shape. And you can see that on the sphere, the charges are uniformly distributed. On the cube, the charges bunch up on the corners. And over here on this oblong shape, the charges bunch up where it's got a sharper curvature than where it's got a wider curvature. Remember when I was talking about the lightning rod and I said that electricity is attracted to sharp points? That's why, because when you have a charged conductor, the charges tend to accumulate in the corners. And the reason for that is that there's a rule that the electric field inside the conductor has to be zero. And so the charges will move and distribute in such a way that that's found to be true. Now, the math that actually proves that's pretty complicated. It uses calculus, so we're not going to go through all of that. But the end result is still kind of interesting. And this idea that charges will tend to accumulate at sharp corners, it's an interesting thing to know. And it's also, as we talked about previously, it's the reason why lightning rods work. Now, we've talked about potential energy before. And there is, as we'll see, something called electrical potential energy. But there's something different called electrical potential. And electrical potential, or electric potential, is simply defined as the electrical potential energy divided by the amount of charge. And the units of energy over charge would be joules over coulombs, but we give that a name. We call that a volt. So 1 volt is equal to 1 joule divided by 1 coulomb. You've probably heard of volts before, and that's what it means. A volt is a measure of electric potential. And so when you go to the store and you buy a 9-volt battery, the positive and the negative terminals of that battery have a 9-volt electric potential difference between them. And we'll talk about what that means and what the consequence of that is as we go through these lectures. But just know that volts are a measure of electric potential, and potential is potential energy divided by charge. Now we're talking about electric potential, and we already said that it is potential energy divided by charge. So let's talk about how electric potential energy works. And in order to understand it, we want to go back to, I think it was way back in Chapter 3 when we talked about regular potential energy, or the potential energy from gravity. And we noted that if you lifted this guy up, you gave him potential energy, and if you cut the string, gravity would cause it to pull back down, and that potential energy would be converted into kinetic energy. It's the same idea with charges here. So here we have a negatively charged object, and these guys might have originally been close together, but I pulled on the string to lift this guy up using this pulley. So this positively charged object is being attracted, and as I do work lifting it up, I'm giving it potential energy. And if I were to cut that string, these guys would be attracted, and this potential energy would be converted into kinetic energy. And if you remember, the amount of potential energy lost as it's attracted would be equal to the amount of kinetic energy it gains, because mechanical energy is a conserved thing. And that works for electricity just as it does for gravity. We've already seen that the gravity force equation and the electric force equation are exactly the same. They just have different letters, but their form is the same. So the potential energy works the same way for gravity as it does for electricity. Now, if we take the potential energy in this system caused by separating these charges and then divide it by the charge of this guy, that's going to be the energy per charge, and that would tell you how many volts there are for this guy at this position. And one thing, if you remember, we talked about how when you're talking about potential energy going into kinetic energy, it's the change in potential energy that's important. How much does the potential energy change in going from here to here? It's the same thing with electricity. We're interested in how much the potential energy is changing. And so there are some rules about changes in potential. If you have a difference in potential or a change in potential between 2 points in space, that creates an electric field in space. And as we've already talked about, electric fields push charges. That's, the electric field's related to the force, either attractive force or repelling force on two charges. And so let me say that again, because this slide's maybe the most important slide in this whole lecture. It's a very important idea. Differences in potential create electric fields, and electric fields push charges. This idea is going to be very important when we talk about electrical circuits later on. Speaking of circuits, in a typical circuit you have a battery, and you might have something like a light bulb or a hairdryer or something, and the battery's sending electricity down the wire to the light bulb or the hairdryer or whatever it is, and the light bulb lights up, the hairdryer blows, the electricity is used in this electrical circuit. And so very often, in order to understand how this relates to the idea of potential, which remember is potential energy per charge, that's what potential is, often we make an analogy to a water pump, because the idea of pumping water through a pipe is very similar to the idea of pumping electrons through wires in a circuit. It's not a direct analogy, it's not exactly the same, but as a metaphor, it can kind of sometimes help us understand what's going on. So let's look at two situations here. I've got this tube here, it's fat on one end and skinny on the other end, and it's filled with water on this end. And we know from previous work that the higher the water level is, the more pressure there's going to be. And so what's going to happen is that the water in this guy is going to go and push through here. And so this water level is going to fall and this water level is going to rise. Until when? Until they're both at the same level. And then it's going to stop moving. Now, if you instead have a pump, so what can happen is the water pressure comes in and it gets pushed up, and now there's an outlet here so the water can then return through this pump. The pump pumps it up to this height, giving it potential energy, then it can be poured back into the reservoir and the whole process repeats. And so the pump is maintaining this pressure difference to keep the current of water flowing through these pipes. It's similar to how a battery works. A battery maintains the potential difference, not the pressure difference, but the potential difference to keep driving the electrons, the electric charges, through the wires. And it's a very similar kind of process. And so here we have a basic electric circuit. We have a battery connected by some conducting wires to a light bulb. The electricity flows out of the battery through the wire into the light bulb, which uses that electricity to create light and heat, and then the electricity continues and it returns through the battery. Now, when I say that this battery is 1.5 volts, that's the potential difference between the positive terminal and the negative terminal. And we've already seen that potential differences make electric fields. And so that's going to make electric fields that are lining up with this wire. And so what's going to happen is those electric fields are going to start to push charges through the wire. Now let me be very clear, because a lot of people think that the charges are inside the battery and they're being squirted out of the battery like a squirt gun. That's not the case. The charges are in the wire. What the potential difference does is it creates an electric field that applies a force to the charges that are already there, and so those charges start moving around the wire. And as they pass through the light bulb, they light it up. So remember, the potential difference of the battery is creating electric fields, and the electric fields are pushing the charges around the circuit. Now, remember what voltage means. Here I've reminded you that voltage is energy per charge, and the units, 1 volt, would be 1 joule. Remember, joule is the energy unit divided by 1 coulomb. So what does it mean if we say this battery is 1.5 volts? Well, these charges, as they're going through the wire and they get back to the battery, they sort of get pumped in quotes, through the battery. And what happens is the charges going through the battery, they gain energy. How much energy? Well, for every coulomb's worth of charge, they gain 1.5 joules if it's a 1.5 volt battery, because 1.5 volts would be 1.5 joules per coulomb. So every coulomb's worth of charge gains 1.5 joules of energy. Now what happens is the current goes through the light bulb, that energy gets used up by the light bulb to make light and heat. And so the energy is gained going through the battery, and then it's given off by the light bulb. And so it's used up by the light bulb. But remember, voltage is energy divided by charge, energy per charge. Now here we can see these two models side by side. We have the electrical model and we have the water pump model. And so you can see that you have the pump, which acts like a battery, which is driving the water through the pipe. There's a valve, and you could tap down this valve to stop the water from flowing. In electrical terms, we have a switch. And of course, you guys know there's a light switch on the wall. If you flip the switch, the current flows to the lights and the lights turn on. If you flip the switch in the other way, the lights turn off, because flipping the switch off stops the flow of current. It literally, when you flip a switch like that, it literally makes a gap in the circuit so the current can't flow through it anymore. And if you close the switch, you complete it, and so that the current can flow through it. Now, I didn't draw it, but the book could have drawn a little light bulb here to represent the resistance, but this is actually the way that we draw an electrical schematic and indicate a resistance. This is the symbol for a switch. This is the symbol for a resistor. Now, oddly, they've actually drawn a picture of a battery here. There's a schematic symbol for a battery that you could draw if you wanted to. So the way that you draw the schematic symbol for a battery is it's a long line and a short line that are part of the circuit. And so if this were my battery, I could also draw in the switch, which is like that, and I can draw in the resistor like that. And so I'd have a switch S, I'd have a battery with a voltage V, and I'd have a resistance with a resistor R. But that's just sort of a picture way of representing an electrical circuit. And we'd actually call this this guy over here is an electrical schematic. Now, I've been using this word resistance and I haven't really explained what it means. So, different materials respond differently to the flow of electricity. Some materials let electricity flow easily, and we call those materials conductors. So, a conductor is a material that allows charge to flow freely through it. Other materials don't let electricity flow through them very easily, and we call those things insulators or resistors. Both of those words can be used more or less interchangeably. But when you're talking about an electrical circuit, usually you use the word resistor. But once again, conductors allow electricity to flow. Resistors resist the flow of electricity. Now, they don't stop it. They just make it harder for the they make it more resistance or harder for the electricity to flow. Now, you might have heard the terms AC and DC with regards to electrical circuits, and those are, in fact, the two kinds of electrical circuits. DC stands for direct current. And a direct current circuit is one that's driven by a constant voltage, usually a battery. In my lab, I have a power supply that puts out constant voltage, but it plugs into the wall, so I don't have to replace it when it goes, batteries you have to replace, they get worn out. Also, the nice thing about my power supply is it provides a constant voltage, but I can change how much that voltage is. In other words, I can go to the store and buy a 1.5 volt battery that battery is just going to give me 1.5 volts. My power supply has a little knob on it. It lets me turn up 1.5 or 3 or 6 or however many volts I need. So that is the characteristic of a direct current circuit. The voltage is constant. The other thing that's characteristic of a direct current circuit is the charges all flow only in one direction. Now, in an alternating current circuit, that's driven by a varying voltage. The voltage is increasing and decreasing regularly. And the consequence of that is charges flow in alternating directions. So I've drawn another little circuit here, but in place of the battery, I've actually put in a generator right here. This is a schematic symbol for an alternating current generator. But the key thing is here is that when it's AC, the current's going to slosh this way, and then it's going to go the other way, and then it's going to go this way, and then it's going to go the other way, and it's going to keep vibrating back and forth in that sort of a fashion. So the current goes in this direction and then it goes in the opposite direction. That's what it means when we say the charges flow in alternating directions. And here you can sort of see the current depicted as a function of time. In the DC or the direct current case, the current's just constant. It's going in the same direction. It keeps the same amount. If you've got it hooked up to a 5-volt battery and it's pushing out 1 amp of current, it's just going to be 1 amp of current. If, on the other hand, you have it as an alternating current system, so it's hooked up to a generator, the current and the voltage are going to be going up and down and up and down and up and down. And that's the difference between AC and DC current.